Hello everybody, this is Dr. Christopher White and welcome to part 3 of Plate Tectonics. So I think we can agree by now that there's a reasonably strong body of evidence to show that the continents were once joined together to form a supercontinent. I think we can also agree that there's a reasonable body of evidence that shows that the pieces of crust that make up the Earth's surface are moving. And so obviously we can then combine those two ideas together and say, right, there was this supercontinent, and clearly at some point the supercontinent fell to pieces and the continents moved to their current positions. So the next step is this. Well, if we can agree that there is one supercontinent that existed in the past, were there any more? And the answer is yes. Geologists think we can account for 5 supercontinents during Earth history. So I'm actually just going to jump to the next slide. So the oldest supercontinent that we think existed was Nuna. So Nuna was around between about 2 and 1.5 billion years ago. So you'll notice that Nuna, to the best of our knowledge, was situated north of the equator, in a position between the pole and the equatorial plane. Now, Nuna was around for 500 million years, it fell apart, and then about 400 million years after Nuna fell to pieces, we got Rodinia. So Rodinia was around between about 1.1 billion and 750 million years ago. Notice in the case of Rodinia that most of the continental landmass is actually located along the equator. Now this becomes very, very important later on because the positioning of all the continents along the equator has a very, very significant effect on the global climate during the Proterozoic. We're going to be discussing that in a few lectures' time. So Rodinia fell apart about 750 million years ago, and a new supercontinent formed actually quite quickly afterwards. So that was the supercontinent Pangaea, and that formed, about 125 million years after Rodinia fell to pieces. So it was actually quite a quick collapse, and then the continents coalesced together again to form the new supercontinent. In the case of Pangaea, the position of it is a little bit difficult to work out. So where it exactly sat on reference to the poles and the equator is a little bit tricky to know. Oh, I actually went the wrong way there, sorry. So then after Pangaea, which fell apart about 560 million years ago, we had the formation of Gondwana and Laurasia. So these are actually 2 separate supercontinents. So Laurasia is located in the northern hemisphere, and it consists of North America, Europe and Asia. Gondwana over here is in the southern hemisphere, and that consists of South America, Africa, India, Australia and Antarctica. And so these 2 supercontinents were separate from one another, and they were moving around between about 510 and 300 million years ago. Around 300 million years ago, Gondwana makes contact with Laurasia, and the 2 lock into each other, and that leads to the formation of the supercontinent Pangaea. So Pangaea is the most recent supercontinent that we know of, and so Pangaea was around until about 175 million years ago, at which point it was really beginning to fall to pieces. So you can also argue, by the way, that there is an argument to be made that we actually do have maybe a couple of supercontinents now. You could argue that Europe, Asia and Africa are forming one supercontinent at the moment, and you could argue that North America and South America are also forming another supercontinent right now. That's kind of debatable. Most people don't classify them as supercontinents. However, from a purely scientific point of view, a supercontinent is when you have 2 or more land masses joined together. So in theory, North and South America would technically count as a supercontinent, even though they aren't normally described as such. So the next question is well, okay, we can see there have been supercontinents in the past. Well, what's probably going to happen in the future? Well, the predictions about what's going to happen in the future will be based on the current tectonic situation and predictions about what we think is going to happen with global tectonics. So, for instance, we can say with a relatively high degree of certainty that Africa is going to keep moving north, and it's going to eventually hit Europe, and it's going to create a very large mountain range. And now we really will have a supercontinent here: Africa, Europe, and Asia, and India, in fact, all together as one very large supercontinent. We can also say with a relatively strong degree of certainty that a subduction zone is going to open up on one or both sides of the Atlantic. It's uncertain which side of the Atlantic it would open up on, but in this particular image up here, they've decided to go for the western side of the Atlantic, so essentially down the eastern seaboard of North America and South America. And of course, this would mean that the Atlantic seafloor would be subducted and destroyed, and that would steadily bring the supercontinent over here, this mixture of Europe, Africa, and Asia, would steadily move this way, and obviously, eventually, it would make contact with North and South America to create the supercontinent that we see here. And those are relatively, probable that's a relatively probable tectonic situation. Now, as for Australia and Antarctica, that one's a little bit more difficult to work out what's going to happen. In these particular models, they appear to be predicting Antarctica is going to move northwards, and Australia's going to kind of stay pretty much where it is. Eventually, according to this particular model, it will make contact with Antarctica. I'm not 100% sure about that one. So that one's probably a little bit of an educated guess, but the landmass we see here is very likely to form in the future. Okay, so we've come to the conclusion that the Earth is covered in plates. These plates are moving around, and sometimes, they will bang into each other. Sometimes they'll move away from each other, and sometimes they'll just move past each other. So once we know that the surface of the Earth is covered in these plates, we need to start thinking about, right, what exactly do their interactions produce? So to begin with, we can see this diagram here is showing you the positions of the plates as we know them now. It's also showing you, using arrows, the directions in which the plates are moving. So for instance, you can see using these arrows that the Pacific plate is moving in a northwesterly direction. In the case of the Nazca plate, for instance, it's moving in an easterly direction. And essentially, the North American plate is moving westwards, and so on. So once we know we have these plates, we have to think to ourselves, right, when they're moving apart, when they're moving towards each other, and when they're moving past each other, what's going to happen? So we know there are two types of crust. There's oceanic crust and continental crust. So obviously the oceanic crust makes up the majority of the seafloor. The continental crust, shock horror, makes up the majority of land masses, and of course it also underlies the shallow seas along the coast, which the portion which we refer to as the continental shelf. So oceanic crust, seafloor, continental crust, the land masses, and the continental shelf. So oceanic crust is actually relatively thin. It's only about 5 to 8 kilometers in thickness. In contrast, continental crust can be anywhere between about 10 and 70 kilometers in thickness, so there's quite a big difference there. Now, this is obviously going to cause a difference in height, because if you think about it, so think of the oceanic crust as a block of wood, and you put it in the water. Well, that block of wood, let's say it's an 8 kilometer thick block of wood, and it's sitting in the water. Well, in order for that block of wood to be stable, 4 kilometers of the wood need to be underwater, and 4 kilometers of the wood would be above the water level. Yeah, in that way the piece of wood would be stable. So that would mean that 4 kilometers of the wood would be above sea level. Now, think of the continental crust. Let's say it's 70 kilometers thick. Well, that would mean same situation. You've got a 70 kilometer thick piece of wood, put it in water. 35 kilometers of that would be below sea level, and the other 35 kilometers would be above the water level. So the continental crust, because it's thick, is naturally going to sit higher than the oceanic crust. So that's why the continents naturally form highs and the oceanic crust naturally form lows. And so the oceanic crust, because it forms the low, well, that's obviously the area that's going to fill in with water, because we are lucky on planet Earth, we have loads of water moving around, and so that water is going to naturally congregate into topographic lows, of which the largest topographic lows are the ocean basins. Another reason the oceanic crust sits lower than the continental crust is also because of its density. So oceanic crust compared to continental crust is actually quite dense. It's heavy. Continental crust, on the other hand, when compared to oceanic crust, is lighter. And so once again, because the continental crust is lighter, it's naturally going to float a little bit more easily on the asthenosphere. and so it's going to sit that little bit higher than the oceanic crust. Once again, that's going to contribute to this difference in topography. The continental crust is going to stand high, the oceanic crust is, comparatively speaking, going to be a lot lower. And then finally, there's the material the crust is made from. So oceanic crust is made from a mixture of basalt, gabbro, and peridotite. So the basalt essentially represents the top of the oceanic crust. That's the area that would be, the sea floor itself, the bit you could actually walk on. The gabbro represents the magma chambers underneath the solid crust. That's actually, which has the magma to actually feed the creation of new crust. And the peridotite represents the material that's melting to form the magma, which goes into the magma chambers, and the magma chambers eventually cool down to form the gabbro. Don't panic, I'm going to show you a picture in a few slides' time that's going to make that a lot clearer. In terms of continental crust, well, continental crust consists mostly of granite, gneiss, so remember gneiss is a metamorphic rock. Compositionally speaking, it consists mostly of quartz and feldspar and a few ferromagnesian minerals. So, in terms of what it's made from, it's actually very close to granite, so they're very similar rocks. And granodiorite. Granodiorite is an intermediate igneous rock, so it's not quite as rich in potassium feldspar and sodium plagioclase feldspar, but it's slightly richer in things like calcium plagioclase feldspar and has a little bit more of the ferromagnesian minerals, but it's not, but it's still a very feldspar dominated rock. So the continental crust is made from intermediate and felsic igneous rocks and very feldspar rich metamorphic rocks, whereas in comparison the oceanic crust is made from mafic and ultramafic rocks, and that obviously explains the density. Mafic and ultramafic rocks tend to be heavier than the more felsic and intermediate igneous rocks. So when the the plates are separated by three types of plate boundary. So there are the plate boundaries where the plates are moving apart from one another. Those are referred to as divergent plate boundaries. There are the plate boundaries where plates are coming together and crashing into each other. Those are the convergent plate boundaries. And there are the plate boundaries where the plates are simply moving past each other. Those are the transform plate boundaries. And you can see that for divergent and convergent plate boundaries, there are subgroups. Okay, so what is actually the driving force behind plate tectonics? So when it really comes down to it, plate tectonics is driven by mantle convection. So what we have is the same kind of situation that we get occurring in a pan of boiling water. So down here at the base, the mantle gets hot. Because it's hot, it naturally becomes buoyant, and so it rises. As it rises, it steadily gets cooler. As it gets cooler, it begins to become less buoyant, and so because it loses buoyancy, it starts to sink, and so we get these convection cells forming in the mantle, where hot mantle rises and cold mantle sinks. So straight away we have these convection cells moving, and those convection cells are naturally going to pull the crust along with them. So this piece of crust here is going to be moving along with the convection cell. The other thing is that when you have two convection cells running along with each other, so we've got this convection cell is coming up here and going this way, this convection cell is coming up here and going this way. Well, that means this piece of crust over here is going to want to go off to the left, whereas this piece of crust over here is going to want to go off to the right. This means this bit of crust right here in the middle is going to be being stretched in both directions, isn't it? And of course, as you know, crust is solid, so it doesn't stretch, it breaks. And so these are the locations in which we're going to form the divergent plate boundaries, because the crust is naturally being stressed by one convection cell going this way and one convection cell going this way. Okay. In the case of subduction zones seem to be associated with areas where the mantle is actively going downwards. And this isn't a huge shock. So what we have here is new crust is being made at the spreading ridge. The crust is moving laterally away from the ridge. It's hitting the continental crust, and the mantle is descending here, and so it helps to pull the crust down with it, the oceanic crust down into the mantle as it goes. So mantle convection appears to be one of the contributing factors to plate tectonics. Now the next question is well, why is the mantle convecting? And the mantle is convecting quite simply because it's hot. There's lots and lots of heat in the Earth's interior, and that heat comes from two sources. The first one is the obvious one, radioactive decay. So the Earth's mantle is absolutely stuffed with radioactive isotopes, so things like potassium 40, thorium 232, uranium 235, and uranium 238. And these isotopes are constantly breaking down, they're decaying radioactively, and of course, as part of that process, they release huge amounts of heat. The other contributing factor to the Earth's internal heat is what's called the heat of accretion. So if you remember, all the way back in the first lecture, we were talking about how the planet Earth formed from lots of bits of rock accreting together, so sticking together. Well, when those pieces of rock stuck together, they didn't just stick together gently, they would smash into each other. They would hit each other head on, and they would merge to form a new piece of rock. So this process of pieces of rock hitting each other, that's not a gentle process. It's a powerful, energetic event. And some of that energy, when the impact occurs, will be turned into heat energy. So think about it. If you have if you have billions or trillions of these impacts that go to form the Earth, well, each one of those impacts is going to contribute a small amount of heat energy into the Earth. And so when you do that times 1 trillion, well, that's going to be a lot of heat, isn't it? So we also have this thing we call the heat of accretion, and that's the residual heat from all the impacts that went to form the Earth. So from these two sources, that helps to explain, why the Earth's interior is hot. And obviously once we know it's hot, well, we then know that hot mantle will rise and cold mantle will sink. And so we get these convection cells. So the next question is well, if the mantle keeps producing heat, it's going to keep getting hotter and hotter and hotter, isn't it? And eventually, if the mantle got too hot, bad things would happen. And actually, in the last 2 slides of this presentation, I'll show you an example of what bad things can happen if the mantle gets too hot. So in order to stop the interior of the Earth overheating, the Earth obviously has to lose heat. So the question is how does it lose heat? Well, it loses heat in 4 ways. The first way is it loses heat at spreading ridges. So underneath these divergent plate boundaries, we have mantle rocks melting to produce magma. And so that magma rises through the crust, cools down and solidifies to form new oceanic crust. So what's happening is you're taking heat from inside the Earth, using it to melt rock, and then transferring that heat to the surface where it's lost to the oceans and the atmosphere. And so that's one way of getting rid of heat. The other way we can get rid of some heat is by subducting cold oceanic crust. So this oceanic crust here, subducting down into the mantle, is going to be, comparatively speaking, quite chilly. And so it's just going to be like dropping an ice cube into your cup of coffee. It's going to help to bring down the temperature a little bit. Obviously, the simplest way of losing heat is through conduction. So heat will simply conduct through the crust and then be lost to the atmosphere or the oceans. Most of the heat is conducted through the oceanic crust because it's the thinnest. Remember, continental crust can be up to 70 kilometers thick, so it doesn't conduct heat, hugely effectively. Oceanic crust is only about 5 to 8 kilometers thick, so heat can, so the heat can transfer through it relatively fast. And the final way are mantle plumes. So a mantle plume forms right down here at the core mantle boundary. So we have an area of mantle that gets superheated, it's stupidly hot, and so the mantle melts, and the resulting magma comes flying up through the mantle, and it gets stuck at the base of the crust. And we see mantle plumes because we know mantle plumes exist because they create these linear island chains like the Hawaiian island chain. So that's also another way of taking heat from deep in the mantle, transferring it up, and obviously getting rid of that heat in the form of magma, which gets pushed out onto the Earth's surface. So these are the methods by which the Earth's interior helps to maintain balance. Okay, so now let's think about our different types of plate boundaries. So we're going to start off with constructive plate margins, also called divergent plate boundaries. So divergent plate boundaries come in 4 stages: stage 1, stage 2, stage 3, and stage 4. So stage 1 typically is focused on a piece of continental crust. So you'll have your piece of continental crust, and your continental crust will be sitting above 2 different convection cells. So remember, the mantle is rising up, convecting and coming down. So it's convecting one way, and on the other side it's convecting the other way. And so because this area of mantle here is going to the left, and this area of mantle here is going to the right, it starts to stretch this piece of crust in the middle. So this area here is under what's called extension. It's being pulled. So the rocks are being stretched. And once again, as we know, rocks behave in a brittle fashion, so when they start getting stretched, they don't, they don't get drawn out like a piece of silly putty, they break. The other thing is that because we have these two convection cells, I'm just going to go back to the previous picture here. So we have a situation like this. So we have one convection cell coming up here and one convection cell coming up here. Now, if there is something like a mantle plume forming, it's naturally going to be channeled up here between these two convection cells. And so this means that you'll also get large amounts of magma gathering underneath this divergent plate boundary. So we not only have the convection cell pulling this piece of crust this way and this piece of crust this way, we also have magma naturally pooling at the point where these two convection cells meet. And so this magma is obviously hot, it's buoyant, it wants to rise, and so it starts to cause the crust to dome. This stretches the crust even more. And so this area of the crust here is being stretched, it's being heated, and of course it begins to fail. Not really a huge shock there. And so obviously when it begins to fail, it begins to crack. Of course we know by now these cracks are referred to as faults. So we have blocks of rock moving past each other, and these faults make the perfect pipe work through which the magma can move to the surface. So what happens then is we move on to stage 2. Now this is the point where we form something which is referred to as a rift valley. So what's happened is this piece of crust over here is trying to move to the right, this piece of crust here is trying to move to the left, and obviously as we know this area in the middle is being stretched, it's being extended. So we know the crust will fail in a brittle fashion, it will break, and that means the crust will split up into these chunks of rock. And these chunks of rock will essentially move relative to each other, and because this piece of crust is moving this way, this piece of crust is moving that way, the rock that's in the middle here drops down to fill the gap. And so we end up forming this topographic low, this valley. Okay. Now, obviously, as we also know, the valley is going to fill with volcanoes because we have all this magma down here, and some of that magma is going to make its way along these fault plains to the surface, and it's going to be erupted onto the surface. And then the final stage is eventually this piece of crust here is going to get very, very thin. So if we go back to the rock presentation when we're talking about igneous rocks, you'll remember there's a form of a form of melting called decompressional melting. And that's when we take a piece of rock which is very, very hot but under very high pressure, and we suddenly decrease the pressure. And if you remember, when we decrease the pressure quickly, that hot piece of rock will suddenly melt. And so what we have here is we have an area of rock directly below this rift valley that's all of a sudden finding itself under much lower pressure. Because remember, this piece of continental crust here can be anywhere between about 10 and 70 kilometers thick. This bit of continental crust here, because it's, being stretched out, it's now, it's much, much thinner. And so that means the mantle rocks underneath the rift valley are under much lower pressure, but they are still very, very hot. And so the mantle under here will start to melt. And so what we'll see is we'll see the magma here beginning to melt, so the peridotites will begin to melt, and that will start forming mafic magma. And if you remember, mafic magma is what goes to form rocks like basalt and gabbro. So eventually we reach the point where the crust has been stretched so far that the mantle really begins to melt. At this point, this mafic magma is going to start making its way to the surface. It's going to start cooling, and now we have oceanic crust forming. Because remember, oceanic crust forms from mafic magma, so it's made of basalts and gabbros. So as these mafic magmas make their way towards the surface, cool and solidify, we start to form oceanic crust. And so what's going to happen now is we have our piece of continental crust. This piece has gone that way, this piece has gone that way, and now in the space between the two, we're going to start forming oceanic crust. So, of course, we've already discussed how oceanic crust is denser than continental crust, how it's also thinner, and so that means our oceanic crust is naturally going to form a topographic low, and of course that topographic low is going to start filling with water, and it's going to produce essentially a very narrow seaway. And then finally, over time, this seaway is going to become wider, and it's going to essentially widen to the point where we now have an ocean basin. So a good example of an ocean basin is, of course, the Atlantic. So running down the middle of the Atlantic, we have the Mid-Atlantic Ridge where new crust is being created. And obviously, if we're thinking about the Atlantic, North America would be over here, and Europe would be over here. and the Mid-Atlantic ridge and down the middle of the Atlantic Ocean is creating the oceanic crust that's pushing Europe this way and North America that way. So the question is well, can we see these stages occurring on the surface of the Earth now? And the answer is yes, we can. So here we are. So this is the East African Rift Valley. So what we can see is we have several different areas. We have the Red Sea, we have the Gulf of Aden, and we have the East African Rift Valley here and the West African Rift Valley here. Okay, so this area is beautiful because it helps to essentially cover all four stages of divergent plate boundaries. So the West and East African Rift Valley, they represent stages 1 and 2. So the crust is actively being stretched, and the stretching is occurring in these red zones here. So the crust is being extended, and that's causing the crust to thin, and it leads to the formation of rift valleys. And I'm just going to skip to the next picture, and you can actually see the rift valleys here. So you can see here's the East African Rift Valley coming down there, and here's the West African Rift Valley coming down here. The good thing is, of course, because the Rift Valley forms a topographic low, it tends to, if there's enough water around, it tends to get filled with lakes. So we can actually see the West African Rift Valley quite nicely right there. In terms of the East African Rift Valley, conditions are a little bit drier, so you don't really get huge bodies of water forming, but you can pick it out because you can see, it's slightly hilly compared to the terrain either side, which is nice and flat. This area looks rather uneven because, of course, it's covered in volcanoes. If we zoom in even further, we can actually see, so this is a picture of an area of Kenya. Now, these white dashed lines here represent the approximate position of the Rift Valley. And it's a bit difficult to see, but can you see how this picture shows these kind of almost like striations running north-south? Well, these are these faults being produced as the crust is extended. So this piece of crust here on the west is trying to move off to the left. This piece of crust here on the right is trying to move off to the east. And that means this area of crust here in the middle is being stretched. And as we said, when you try and stretch a piece of solid crust, it breaks. And so we can see these fractures in the form of these very, very long linear faults which are on the surface. So the East and West African Rift Valley covers stages 1 and 2 of the formation of a divergent plate boundary. The Red Sea is a perfect example of stage 3. So what we can see when we look at the Red Sea is we can see we have this narrow seaway, which is exactly what we have here. And in the middle of the narrow seaway, we have the formation of oceanic crust. So if we look at this picture here, now this is a topographic image. The more dark blue and purple the color is, in the case of the Red Sea, the deeper the water. So the light blues and greens, that's shallow water. These blues and purples here, that represents deep water. So this is our rift. This is the location where new oceanic crust is forming, and it's just started. You can kind of see it here in this picture. This kind of light purple area here represents the region in which we've just started to form oceanic crust. So the Red Sea represents stage 3. We've just started to form new oceanic crust, and so it's pushing one piece of continental crust that way and the other piece of continental crust this way. So if we go back, the Red Sea is going to, well, if it has time, it will start creating new crust. It's going to want to try and push Africa to the west, and it's going to try and move the Arabian Peninsula off to the east. Finally, once a divergent plate boundary begins to become established, it will start to push the pieces of crust even further apart, and we'll start to form ourselves a proper ocean basin. So that's the Gulf of Aden. So the Gulf of Aden, as you can see, is much, much wider than the Red Sea, but that's because it's more advanced. So if we just go to the next slide here, we can actually see this is the Gulf of Aden right here. So this is, once again, it's a topographic image of the seafloor. Once again, the bluer the colours, the deeper the water. Now, I probably could have picked my colours a little bit better, but you'll see there is this zigzag shape here, this zigzag line. Okay, some parts of it I've marked in red and some parts of it I've marked in yellow. This is the divergent boundary where new crust is being made. So what you're thinking, well, what's this zigzag pattern? Well, if we just go back here to stage 4, we can see that our nice linear divergent plate boundary actually splits up into these separate pieces. And that's because oceanic crust is not created at the divergent plate boundary at the same rate. So some parts of the divergent plate boundary will be creating oceanic crust very, very quickly, and some parts will be creating oceanic crust more slowly. And so because you have these differences in rates, it means some parts of the ridge will actually actively move away from other parts, and you'll have this staggered pattern. And the space in between them will be, well, essentially this movement will be allowed through the formation of very, very large transform faults. And so these areas here are where the oceanic crust is being created. And these faults here, now they are not areas where new oceanic crust is being made. They're just faults that allow these pieces to move independently of each other. So you can see we have this stepped pattern, which is exactly what we see here on the floor of the Gulf of Aden. So the red parts here, those are the parts where new oceanic crust is being made. Okay, so this part here, for instance, we have new oceanic crust being made. It's pushing the oceanic crust on this side northwards and the oceanic crust on this side southwards. The yellow lines here, they represent these transform faults. And so the Gulf of Aden is a lovely example of a stage 4 divergent plate boundary. And obviously over time, if conditions are correct, the Gulf of Aden will keep getting larger and larger and larger, and eventually it would lead to the formation of an ocean basin the size of the Atlantic. So the East African Rift Valley system is a perfect example of the formation of a divergent plate boundary. It takes us through all 4 stages, and we have these beautiful examples. So we're just going to quickly do this slide. We're just going to take a second and talk about oceanic crust, and then we're going to stop part 3. So oceanic crust, as I said, is made of 3 different rock types: basalt, gabbro and peridotite. So if we take a slice through the oceanic crust, this is what we see. We have peridotites down at the bottom, gabbros in the middle and basalts at the top. So each of these different layers has its own composition and its own distinct textures. And there's actually 4 individual layers. There's the peridotite, which are the mantle rocks, very, very rich in olivine. We have the gabbros. Now that's a mafic intrusive rock. So it's very, very rich in calcium, iron and magnesium, and it's got a coarse crystal makeup. So you can see the crystals with the naked eye. Now, the upper 2 layers here, the sheeted dike complex and the pillowed basalt, they're made of basalt, and as I'm sure you know, basalt is a volcanic mafic igneous rock, so it's very, very fine grained, so you can't see the crystals. So what's actually going on? Well, we've already discussed that the mantle peridotites here, well, they're very, very hot, but because the oceanic crust at the ridge is very, very thin, it means that these mantle peridotites are very, very high temperature, but the pressure is quite low, so they begin to melt. So that magma that's produced by the peridotite melting is mafic. So that mafic magma rises up and it pools in the crust. So it forms this magma chamber here, sitting directly below the spreading ridge. So some of the magma from this magma chamber will go towards the surface, but a lot of it actually never makes it to the surface, and it just sits there and it cools down and it crystallizes. Well, if you take a mafic magma, cool it slowly, you get a gabbro. So the gabbros we're seeing here represent the rocks produced by the cooling of the magma chamber. Some of the mafic magma will work its way towards the surface, so the mafic magma is going to make its way towards the surface. As it moves through the crust, it's going to push the crust apart, because remember, the mafic magma has to make room for itself. So it's going to find a fault or some kind of weakness, and the magma is literally going to inject itself along that fault, and it's going to push the crust out of the way as it moves through the crust. So what's going to happen is it's going to push the crust out of the way, and the magma is going to rise towards the surface as these sheets. Okay. When the magma cools down, and it will be cooling down as it moves through the crust, it will solidify and it will form a basalt. And so these basalts will form sheet after sheet after sheet. This is the sheeted dike complex. This is actually the region of the crust where the oceanic crust is being forced in two. So this is the region where the oceanic crust gets pushed apart, right here where the sheeted dike complex is located, because that magma has to push its way through, and it has to push the crust either way to make space for itself. And then finally, some of the magma will actually make its way onto the seafloor, and when it makes its way onto the seafloor, it will form what's referred to as a pillowed basalt texture. And if you want to know what that looks like, go all the way back to the title slide of this presentation. It looks like lines of toothpaste that have almost been squeezed out, one on top of another. And that's the texture we get when mafic lavas are erupted onto the seafloor. And so our oceanic crust consists of mantle peridotite, gabbro, basalt, and basalt. So we have the peridotite, the gabbro, the sheeted dike complex, and the pillowed basalts. Okay, so we're going to stop part 3 here. Do you know what? But we're not going to quite stop yet, because of course we need to do the code word. So what's the code word for this presentation? The code word for this presentation is yellow. Yellow, like the colour. Y-E-L-L-O-W. Yellow. So please write that down. Put it somewhere safe, because you're going to need it for the code word quiz. Okay, once again, get up, have a walk around, go in a glass of water, relax for a few minutes, and then come back for the 4th and final part.